polymers, another word for large molecules. You hear a lot about them with respect to combustibility. This model represents the basic arrangement of atoms in a common polymer. It contains chiefly hydrogen, oxygen, and carbon. When it burns, it gives off acetic acid, formaldehyde, and carbon monoxide, along with at least 20 other toxic materials. The toxic gases from this polymer are responsible for perhaps over 50% of all fire deaths. Its name, cellulose, another name for wood, paper, or cotton. This polymer is also very common. It contains carbon, oxygen, hydrogen, and nitrogen. When this material burns, carbon monoxide and hydrogen cyanide are given off. Hydrogen cyanide is one of the most toxic gases known. The name of this polymer? Wool, hair, and fur. This polymer is man-made. It contains hydrogen, chlorine, and carbon. When heat is applied, this polymer will burn, giving off as primary combustion products carbon monoxide, carbon dioxide, water vapor, and hydrogen chloride. Hydrogen chloride is an irritating and toxic gas. This polymer is known as polyvinyl chloride, or PVC. And its uses range from house and building siding to automobile upholstery. Man is literally surrounded by polymers. The vegetable world is chiefly made up of the polymer cellulose. Along with such vegetable products as wood and cotton. Rubber is a polymer, both natural and man-made. So is leather. Just about every fabric known is a polymer, with the exception of glass fibers. Even clay pigeons are not all clay, but consist of clay held with a polymeric binder, asphalt. Shotgun shell casings are made of a man-made polymer, high-density polyethylene. Even modern gunpowder is a polymer, a chemically modified cellulose known as nitrocellulose. The key ingredient of all polymers is the element carbon. The diamond is one of its pure forms. Another more common form of the element carbon is graphite, the lead in a lead pencil. But the amazing property of carbon, which no other element possesses, is its ability to bond to itself to form complex molecules. Let's look at a few examples. If a single carbon atom is bonded to 4 hydrogen atoms, the result is methane, or natural gas. If 3 carbon atoms bond to 8 hydrogen atoms, the result is propane. Propane is another common fuel gas. If 8 carbon atoms bond to 18 hydrogen atoms, the result is octane. Octane is a component of gasoline. And if carbon atoms bond to carbon atoms in long chains, the result is a polymer. The chain may contain just carbon and hydrogen, as in polyethylene. Polyethylene is a common polymer used to fabricate trash and garbage bags. A polymer may contain oxygen, as in cellulose, have chlorine attached, as in polyvinyl chloride. But whatever variation, the common element is carbon atom joined to carbon atom. If we abbreviate carbon with the letter C and hydrogen with the letter H, to fully type out the structure of a single molecule of polyethylene would require over 3,000 feet of paper and require the services of a skilled typist for nearly 1 month. And yet, in nature, polymer molecules are so small and so narrow that they are beyond the power of the best microscopes to be seen individually. What happens when a polymer burns? How do polymers behave in a fire? All burning consists of reaction with oxygen. And if carbon is present, carbon monoxide and carbon dioxide are formed. Carbon monoxide is the chief hazard, odorless, colorless, and deadly. Carbon monoxide is formed whenever carbon-containing compounds burn, such as when charcoal burns in your backyard grill. Or when gasoline burns in your car. Or whenever polymers burn. The other toxic gases formed depend upon the atoms present and their molecular arrangement in the polymer. In chlorine-containing PVC, hydrogen chloride is given off. The nitrogen in wool forms hydrogen cyanide. Wood, wool, and man-made plastics all are polymers and all will burn, releasing toxic gases. In order to evaluate the hazards from burning polymers, researchers from the B.F Goodrich Company, Battelle Memorial Institute, and the Columbus, Ohio Fire Department conducted a series of full-scale room fires. Tiny tubes and heat sensors led to a battery of test instruments which continually monitored the temperature, oxygen level, and level of toxic gases in the burning room. In this room, furnished with ordinary furnishings, the fire built up and spread rapidly. Temperatures in the burning zone rapidly rose to an excess of 1,500 degrees Fahrenheit, hot enough to melt aluminum and brass. After 6 minutes of burning, the carbon monoxide level suddenly rose from less than 0.1% to nearly 1.4%. At this level of carbon monoxide, unconsciousness will ensue after a few seconds exposure. At the same time, the oxygen level dropped to 10%. This is below the level required to support life. All of these changes occurred in less than 60 seconds. Thus, firefighters should often expect rapid deterioration of the atmosphere near a working fire. In similar experiments considered jointly by NASA and Battelle, an even more deadly concentration of toxic gases was found in the burning of a typical room. These time-lapse films show the progression of a room fire speeded up by a factor of 6. After this fire had burned for nearly 6 minutes, the next 30 seconds saw the carbon monoxide rise to a peak of 8.5%. Such a carbon monoxide level will cause unconsciousness after a single breath. At the same time, the oxygen level dropped to a low of 6%. Polymers, the most common single fuel for a fire. Since all polymers, both man-made and natural, contain carbon, carbon monoxide is always a hazard. Since all burning uses oxygen, oxygen starvation is always a hazard. The best protection, the self-contained breathing apparatus. Canister masks offer no protection against oxygen starvation. For this reason, canister masks have not been generally accepted by the fire services. Whenever man encounters a hostile atmosphere, he carries his own air supply with him. And of all atmospheres in which man has to work, none is more deadly than that near a working fire. To the firefighter, this means bottled air is essential to his survival. Only the self-contained breathing apparatus can offer positive protection against the hazards of carbon monoxide and oxygen starvation, along with all other toxic gases. The next time you hesitate to wear a self-contained breathing apparatus, remember that the smoke can contain carbon monoxide above 7%. 0.1% is considered harmful. Oxygen levels well below 14%, the minimum required for breathing. Oxides of nitrogen at 3 times the danger level. Sulfur dioxide may be at 7 times the danger level. Hydrogen cyanide at over 8 times the danger level. Hydrogen chloride and other gases also at dangerous levels. Wood, wool, and man-made plastics. All are polymers, and all will burn, releasing toxic gases. To the firefighter, the self-contained breathing apparatus is his best protection.